Today in Chem 100, we're going to review materials for exam number 8. That's chapter 16 in your textbook. And the topics covered are acids, bases, and pH. Actually, we touch on buffers also. But this review session is going to use your homework application from Cengage. And I need to share that screen. Let's see if I can just find it. Let's see, we're going to show all windows and there it is. Okay, come on. There we go. Okay, so here's our Cengage homework, and this is what the instructor sees. All these things on the right, of course, are those questions that you need to answer for your homework score. Everything on the left is what I left out, and there are a lot of questions that are available. So we're going to use these that weren't part of the homework to review this material. And then this is Thursday, so next Tuesday we'll have another review, and we'll work from the review document that's in Blackboard. So hopefully with this 1-2 punch, we'll get everything covered and help you feel more comfortable with the material. All right, so we're going to take the difficulty level 1 first, and we'll work our way down and find unique problems to work. If we find a duplicate, we'll skip it. And then we'll run back and we'll get the difficulty 2s and the difficulty 3s. And if there are any 4s, we'll do those too, because I'm pretty sure we'll have plenty of time. So let's start with the first one. And let's see. This is going to be, well, this won't have a number because it's this chem work section. So conjugate acids and bases is the topic. Let's read the question. It's important to understand what the question is asking for. Choose pairs from the following in which the first listed ion or compound is the conjugate acid, is the acid, and the second one is the conjugate base. Okay, so we have to have the acid first, the base second. If we have the base first and the acid second, they don't want that. That would be a wrong answer. Okay, so we have HPO4 2 minus, HPO4 2 minus, and that's paired with H2PO4 minus. Okay, if this is the acid and that's the base, according to Bronsted and Lowry, what is an acid? An acid is a hydrogen donor, a proton donor. So this would have to lose 1 proton. If this is the acid, then it would have to lose 1 proton, and then what's left over? PO4 3 minus. Notice the charge incremented another negative because we took a positive away here. So the balance has to be maintained. This one plus that 3 minus gives you 2 minus. We've preserved the charge and we've removed the hydrogen, so that is the conjugate base. Not that. Now, if this had been given first as the acid, then yes, going that direction, losing a proton there, would have given you the conjugate base of that as an acid. But this is not the conjugate base of that acid. That is the conjugate base. Right? So the first selection is false, cannot be. So we won't check it. How about the next one? A proton and the hydroxyl. This is supposed to be the acid. This is supposed to be the conjugate base. All right. That's kind of silly though, isn't it? If this loses a proton, there's nothing left. Right? So that can't be it either. That's kind of a silly question, but it does test your knowledge. I'll give them that much. Okay, how about this one? C2H3O2. C2H3O2 minus. This is supposed to be the acid. And this is listed as the base. Right? There are no protons to be lost from this one. You may recall when we write an acid, we put the dissociable protons first. So there should be one out here, and then the rest of the molecule. Like this one. That would be the acidic proton, we call it. So if we're going back this direction, that would be acid base. But we're going this direction, that's acid. That is not the conjugate base. In fact, this one doesn't have a conjugate base because those hydrogens cannot be released. They do not dissociate in water. So this third one is wrong also. Let's see, we got one more. So by process of elimination, I would expect the next one to be true. Let's see. There. If that is the acid, then we should dissociate a proton and leave us with hydroxyl. So the charge is balanced and the numbers of hydrogens and oxygens, they balance. This is the only one there that is an acid base, an acid conjugate base pair. And why does it say that? Maybe I read the question wrong. Choose pairs in which species listed first is the conjugate base. Okay, I read it backwards. So what we have is this one, and this one are all correct, and the last one is wrong. Let's do another one. Let's try another version. All right. Let me read the question correctly this time. Choose pairs in which the first listed, the species listed first is the conjugate base. All right, there we go. And the second one of the species listed second. Okay, so this first one, that acetate ion is the base of this acid. It lost one proton. How about this one? If this is the acid, it can't be because there's no proton to lose. So that one's true. This one is false. If this one loses a proton, it will produce S2 minus. That one is true. If this one loses a proton, it would be CH3NH minus. So that's wrong. This is the acid and this is the base. Right. So those are the only two that are correct. All right. I finally got one right. Okay, so that was difficulty one. Let's go down. Here's another difficulty one. Let's see if there's anything to be gained here. Yeah, some of these questions might introduce minor topics that we did not cover in class. So this is a good thing. And this is one of them. What are some physical properties that historically led chemists to classify various substances as acids and bases? Right. So since we didn't cover it in class, I'm going to have to use this as a teaching moment. Acids were recognized primarily by their sour taste. That's true. Acids are sour. right? Acids are not bitter. Acids are not bitter. So it's either this first one or this second one. Let's see what else is in there. Bases were recognized by their bitter taste and slippery feel. That is also true. Acids are not slippery feel. Right? So this one has to be the right answer. And of course, you don't want to use this method for just anything you pick up. I mean, only babies put everything in their mouth. Hands, feet, whatever is near, toys, even pet cats or dogs that put in their mouth. We don't want to do that because an acid may taste sour to begin with, but if it's strong enough, it'll also eat a hole in your tongue. And bases will do damage also. So this is only valid for very, very, very weak dilute acids and bases. For instance, vinegar on your salad. It tastes sour. Most medications will have a bitter taste. Not all, but very many of them do. And they're bitter because they're bases. And you'll notice that if you use bleach, sodium hypochlorite, if you use bleach and you don't wear gloves, which is not advisable, but if you do, you'll notice that when you get that bleach on your hands, it feels very slick, slippery. That's because this compound is basic. It produces in solution basic pH, a pH greater than 7. Now there's some proposals why it feels slippery. Well, they're beyond this course. Let me just put it that way. And we're not going to spend any time on that. All that information is available on the internet anyway. Okay, so that should be the correct answer. Okay. Let's see if this one is different. Which of the following do not represent a conjugate acid-base pair? Okay, this will be like a review. I said I was going to skip the repeats, but review and repetition sometimes is a good thing, especially since I made a mistake on that first one. Which one of these is not a conjugate acid-base pair? Now, in this case, it doesn't matter what the order is. Right? You could have the acid first, or you could have the base first. Generally speaking, if we say acid-base pair, the acid will come first. And it looks to me like that's the case here. Each one of these is an acid. And we're going to see if the second one is the conjugate base. So HClO, I think that's a 3. No, it's not. HClO. HClO. That's hypochlorous acid. Should be like this. Okay. And notice that we're using the abbreviated version of this dissociation. We're simply removing a hydrogen rather than reacting it with water, which is actually what happens in solution. You would have a water molecule here. This would transfer its proton to the water and give you a hydronium ion along with the conjugate base. But this is acceptable for simplicity's sake. All right, so is the base ClO minus? No, ClO2 minus. So this one is not, do not represent conjugate acid-base pair. So that one satisfies the conditions of the question. How about this one? HiO3. HiO3. If this were This is iodic acid. So we should have a conjugate base that looks like that. Is that the case? No, that's IO4. Remember, two conditions are required to have a conjugate acid-base pair. One, the core must remain. During the reaction. So what is the core? Well, the core is whatever's left after the hydrogen is gone. So if we take a hydrogen away, we have to have IO3 left over. That's why it's over here. In this case, IO3 becomes IO4. That can't be. The second condition is only one proton at a time. Okay. All right, so this one is false. How about HBr and Br minus? That's true. HBr is the acid, Br minus is the conjugate base. So we don't check that one. How about H2PO4 minus? H2PO4 minus, yes. So what would this one do? Dissociate one proton and leave us with a HPO4 2 minus. HPO4 2 minus. So is that the case? H2PO4 minus, HPO4 2 minus. That's also a conjugate acid-base pair. So the first two are false, the second two are true. All right. Let's see, I'm going to scroll up a little bit. Yeah, I can't go too far. Maybe I can stretch it a little bit. Makes more of it visible. There we go. Okay, so that was one. Let's look at difficulty 1 here, see if it's different. Okay, this question has multiple parts. Some of them do that. So I've adjusted the scores for those questions in your homework that have multiple parts. I've adjusted it so that it'll have enough points that can be subdivided and give you credit for each of the parts. Choose the conjugate acid for the following base. Okay, now we're working in reverse. So if this were a base, H3P2O7, H3P2O7 minus, okay? If this is the conjugate base, what would be the acid? You just add a proton, right? So the acid would be H4P2O7 with no charge. Because if you add a proton, a positive charge, it neutralizes that negative. So H4P2O7, H4P2O7 is this one right here. All right. That one's correct. So let's go down to the next one. Choose the conjugate acid for the following base. That appears to be the trend here. SO4 2 minus. So if we add a proton to that, there's only one minus. HSO4 minus. HSO4 minus is right there. Okay, that one's good. Let's try this one. HSE, selenium, HSeO3. HSeO3, 1 minus. So if we add a proton to that, H2SeO, oops. There we go. H2SeO3, right there. Okay, what is that? Well, you remember sulfate. Selenium is in the same family as sulfate. It's a chalcogen. So SO4 would be sulfate. SO3 would be sulfite. This would be selenite. And then it would be selenous acid. All right, so let's check that one. That one's good. And one last one, IO minus. IO minus, add a proton, HIO. Right there, okay? What is HIO? Well, IO, ClO would be hypochlorite, and HClO would be hypochlorous acid. So we stick an iodine in there instead of a chlorine, and we get hypoiodous acid. Okay, all of those were good. We'll see about, here's another number 1. Let's see, is this going to be different or not? What does it mean to say that an acid is strong in aqueous solution? And this question has multiple parts. So when we answer this one, I suspect another one's going to pop up. What does it mean to be a strong acid? Strong in chemical terms means that the molecule completely dissociates into individual ions. And in the terms of an acid, that would be proton dissociated from the conjugate base. And that's complete, virtually 100%. So let's see which one matches. An acid is slightly converted to its conjugate? No. Acid is almost completely converted to its conjugate. An acid's not converted to a conjugate acid, it's converted to a conjugate base. A strong acid is almost completely converted to its conjugate base when dissolved in water. That's true. Okay, so let's see, what's part B going to be? If an acid is strong in aqueous solution, what does this reveal about the ability of the acid's anion to attract protons? All right, that's another way, the ability to attract protons is another way of saying what's the strength of the base. Because in Bronsted-Lowry's terms, an acid donates protons and a base accepts protons. So we're talking about a base here. So if the acid is strong and releases protons very easily, the conjugate base is very weak. It does not attract protons. So a strong acid anion must be very good at, no, just the opposite. A strong acid's anion must be very poor at attracting protons, right? It's the flip side. It's the opposite. If the acid's strong, the base is weak. And that's what this means. It's a weak attractor. It's a weak attractor of protons. So that should be the answer for B. All right. Okay, that's it for that one. So let me scroll down a little bit. Here's another one. Let's see if it's a new topic. Okay, this one's fairly easy. This is definition, right? What is a hydronium ion? It's simply a water molecule with an added proton, which means you have an extra hydrogen and you have a positive charge. So there is your hydronium. Oh, it's multiple parts. Okay. Choose an equation for the formation here. Choose an equation for the formation of hydronium ion when an acid is dissolved in water. So, what do we typically write when we're reacting an acid with water? Well, there's your generic acid, and then there's your water molecule. So we're going to transfer this proton over here, like that. And that leaves us with the hydronium and the conjugate base. Okay, that's the one we're looking for. If it's here. Let's see. There you go. There's your acid here. Let's see, it's not going to let me highlight it. There's your acid. There's the water. And the water behaves as a base. It's a proton acceptor. There's your conjugate base of the acid, and there's your hydronium, which is the conjugate acid of the water molecule as a base. All right. Oh, I haven't been writing the numbers here. That's 16021. Okay. All right. So let's see if 16023 adds anything to the discussion. Organic acids contain the carboxyl group. This is worth doing. 16023. All right. If this is the carboxyl group, like that, there, and there, and something else is attached out here. What you'll very often you'll see in textbooks is if it's written like that, they'll just put something here like that. R can be anything. And the reason we use R is because there's no single letter R in the periodic table. So there's no mistaking it for some other element. Okay, now back to the question. Using acetic acid, and propionic acid, choose equations showing how the carboxyl group enables these substances to behave as weak acids when dissolved in water. Right? So we have one equation for one equation for the other. So for acetic acid, that R group is CH3. And we can write this as COOH, right? COOH. And there's your acidic proton, right? So when you write it like this, and this is common for organic acids, when you write the proton on the end of it, because there's the functional group. That's what we call it. The functional group is the carboxylic acid group. If the functional group is on the end of the molecule, then there's your acidic hydrogen. Okay, how about propionic? For propionic acid, the R group is CH3, CH2. And then the carboxyl group right there. And by the way, during the lecture, I misspelled that. This is spelled carboxylic with a Y, not an I. Carboxylic acid. Okay, so now we want to react these with water, and we look at the choices here, and that's what they do. React it with water. Okay, so let's take a water molecule here as our base. Okay, transfer this proton over here. So both of them will have hydroniums. And then the conjugate base will just be absent that proton, leaving a negative charge behind. So CH3COO minus. And this one will be CH3CH2COO minus. Okay, so let's find the one that fits. Let's see, are they written correctly? That one's okay, that one's good, that one's good. There. Okay, they wrote the acids correctly. Now we got to react with a water molecule. There's a water, all the way down. Okay, the left-hand side, the reactant side is good for every one of them. Now we need to look at the right-hand side. Right, C2COOH. That one's got an H in there. Plus, they took the hydrogen from the wrong place. You can't take a hydrogen from this methyl group. You have to take it from here, right? So that one's wrong. How about the second one? Well, they took the hydrogen from the right place. They just produced the wrong products, right? And that can't be a positive. It has to be a negative. So we don't even need to look at the next one. We don't need to look at that one because this one's wrong. They both have to be right. So here we're adding a hydrogen, right? So in this case, they're saying the water molecule is the acid and the acetic acid is the base, right? And it doesn't work that way. It's the other way around. So let's see. This is the only one left. This has got to be it. CH3COO minus, there, plus the hydronium. Correct. This one should be CH3, CH2, COO minus, and the hydronium. That's the correct answer right there. All right. So now we can scroll down a little more. That was 023. Let's see, how about 037? Does it have anything new to offer? This question has parts. Okay, A part. Why do scientists tend to express the acidity of a solution in terms of its pH? This is a good question. 37. Rather than in terms of the molarity of hydrogen ions present. Okay, we did touch on this subject when we were discussing why Sorensen wanted to do this in the first place. Okay, first choice. The concentration of hydrogen ions and hydroxyls in aqueous solutions don't tend to be expressed in scientific notation. That is false. Absolutely false. They're almost exclusively expressed in scientific notation. The molarity consists, so first one's false. The molarity consists of the numbers from 0 to 14 and can be more easily compared. No, the molarities are not from 0 to 14. See, you have to read that carefully. It's not the molarities that are 0 to 14. It's the pH values themselves that are 0 to 14. pH scale consists of the numbers from 0 to 14 and can be more easily compared. I would choose that one, unless the last one is even better. Let's see. The pH scale consists of numbers which are usually expressed. No, that third one is the best answer. And that's why we use this system. They're more easily compared. Okay, so that's the A part. How about the B part? How is pH defined mathematically? Okay, that should be drilled into your head. pH is equal to the negative log. That's the common log, base 10, of the hydrogen ion concentration. So which one satisfies that? It looks to me like this one does. pH equals negative log of hydrogen ion concentration. Let's see, submit. There we go. Okay, so that was 37. Let's see, we got another number 1, 39. Is it new? Is it different? For a hydrogen ion concentration of 2.07 times 10 to the minus 5, how many decimal places should we use when expressing the pH of the solution? Okay, you just have to know this rule. If we have this one, 2.07 times 10 to the minus 5, and we're looking for significant figures in the pH. How do we do that? The significant figures here, well, actually, we don't call it significant figures in the pH. The pH is a log transformation, and we're actually looking for the number of decimal places. Okay, so you have 3 significant figures here. You can have 3 decimal places in your pH number. Okay, and that goes back to how logs are calculated. Well, let's see. I was 39. That should have been 39. Let's see. How about 49? Is there something new there? This one has multiple parts. Calculate the hydrogen ion concentration in moles per liter for a solution with a pH of 9.78. And it looks like we're doing the same thing. Hydrogen ion concentration for each of these solutions with pHs. Hello. Is everything all right?
Yeah.
Okay. Yeah, I forgot to disable the waiting room. So I had to admit, which is okay. Especially when there's so few students in this class, it's not a problem. So we're up to 49, and we're still looking at difficulty level 1. All right, so if we are given a pH of 9.78, how do we calculate the hydrogen ion concentration from that? Well, you look at the definition of that pH. If it is the negative log of the hydrogen ion concentration, then we say, all right, what does log mean? If this is base 10, that is the power of 10 that equals this. Well, actually, that's not true. There. With that negative sign over here, now this is the power of 10 that is the concentration of hydrogen ions. So we take the anti-log of this number. Anti-log of negative 9.78, which on most calculators is written like this, 10 to some power. So 10 to that power is equal to the hydrogen ion concentration. So I just need to punch that number in, 9.78, change the sign negative, and then do the 10 to the power. All right, let's look at this. How many decimal points are here? 2. 2 decimals means we can have 2 significant figures in our coefficient. So I rounded off to 1.7 times 10 to the minus 10. Okay. And let's see, I'm going to put that in here. 1.7 to the minus 10. There we go. Submit. And it liked that answer. And we can do that for each one of them. By the way, this value, 9.78, means that the solution is basic. The number is greater than 7, so it's basic. And then if you look at the value here, the hydrogen ion concentration, if the solution is neutral, both this and the hydroxyl are 10 to the minus 7. So this is smaller than 10 to the minus 7, means that it's basic. Okay, let's do 6.03. Are we still? Yeah. Let's see. We just need to do this. Like that. So this is going to be negative 6.03. Right. So we'll put in 6.03 and change the sign, and then powers of 10. 9.3 times 10 to the minus 7. Molar. So let's put that in. 9.3 times 10 to the minus 7. Okay. There we go. And 1.71. Is that going to be acidic or basic? Obviously acidic. It's way, way, way less than 7. And that's closer to the molarity of acid in your stomach. .07, did I say? 1.71. 1.71. So we'll do 1.71, change the sign, and take the power. 1.9 times 10 to the minus 2. Okay, punch that in. And we're good there. And the last one, 7.14. So this is just very slightly basic. .14. .2 times 10 to the minus 8. And we should expect a favorable response. There we go. Okay, so that was 49. Let's see, we'll skip these and go to this one, 55, and see if it's something new. When 1 mole of gaseous hydrogen chloride is dissolved in enough water to make 1 liter, which means 1 molar, correct? Approximately how many HCl molecules remain in the solution? We don't even have to calculate this one. We recognize HCl in solution is hydrochloric acid, which is a strong acid, which means there are no HCl molecules left in solution. Okay? That was a logic question, actually. How about 57? This one has multiple parts. This question, calculate the hydrogen ion concentration and the pH of the following solutions of strong acid. Okay? So I'll write the first one up here, and then we can do the others exactly the same way. So this is 57. For the benefit of our viewing audience, we're starting off with 2.35 times 10 to the minus 3 molar HCl. All right. This is a strong acid in solution. What is the hydrogen ion concentration? That is equal to the hydrogen ion concentration because it dissociates, and for every one of these, you can produce one of those, right? There's only 1 proton per molecule. So that is equal to the concentration. So we'll go ahead and put that one in. Okay, and then we'll calculate the pH. Negative log of that number. Equals what? 2.35 times 10 to the negative 3. And then we'll take the log of it and change the sign. Okay, 2.35 significant figures means we can have 3 decimals. 2.629. Is that right? 2.629 pH. Okay. Now we can do the others exactly the same way. So this one is going to be, look at that nitric acid. Only 1 proton per molecule will dissociate. So the concentration of the hydrogen ions is going to be 2.90 times 10 to the minus 3. Okay. And then the pH will be the negative log of that number. .538. 2.538. Because we have 3 significant figures, the pH can have 3 decimal points. Okay. And C. Is this a strong acid? HClO4. That's perchloric acid. So 6.93 raised to the power of negative 4. And then the pH of that 3.159. Okay. And the last one. Oh, another nitric? Yeah, another nitric. All right, so this one's going to 3.40 times 10 to the minus 2. Take the log of that, change the sign. 1.469. Check myself. Yep. Submit that one. Okay. So we got all of those. All right, that was 57. Let's see if 59 has anything different. What characteristic properties do buffered solutions possess? Okay, this is a different concept. In chemistry, what do we mean by a buffered solution? A buffered solution is one in which the pH is actually the pH of the solution resists change when acid or base is added to the solution. So the solution shows only a small change in pH when a strong acid or base is added. That's true. And it says select all that apply, so we could have multiple answers here. A solution is buffered by the presence of the combination of a weak acid and its conjugate base. That's also true, right? And I showed you in class how that weak acid and conjugate base, in equilibrium with one another, how they react to the addition of an acid first and then to a base. The solution resists change in pH only when a weak acid or base is added. False. It doesn't matter. Any acid, any base added, the solution will resist pH change. A solution is buffered by the presence of the combination of a strong acid and its conjugate base. False. Why is that? The reason for that is if you have a strong acid and its conjugate base, what happens when you add acid to that solution? If you add acid, it is not going to combine with this weak base. It has no interest in combining with that one to give you this. So that means you're just going to boost the hydrogen ion concentration. Now, there will be actually there won't be any shift because this is completely dissociated. Actually, there's no return here. That's not an equilibrium situation. So the first two are the only ones that fit. Okay? All right. Let's see, we're on a roll here. Let's see if this next difficulty level 1 has something new to offer. Is it possible for a solution to have hydrogen ion concentration 0.001 molar and OH hydroxyl concentration 4.1 times 10 to the minus 6? Okay. How do we calculate one from the other? Right? They're related in solution, right? So they're derived from the same molecule. Well, not technically, but they're 1-to-1. So if you know the concentration of one, you also know the concentration of the other. because Kw equals this one times that one, right? And if this is equal to 1 times 10 to the minus 14, then if you know this one, you can solve for the other one. So if we say 0.001, which is 1 times 10 to the minus 3, 1 times 10 to the minus 3, what will this one be? We can do that one in our heads. We put this one over here like that. And that means we have 1 times 10 to the minus 11 for that, right? So this cannot be. You cannot have that hydrogen ion concentration and this hydroxyl, no matter what you put in it. So is it possible for a solution to have this concentration? No. Yes and yes, they're wrong. No, for any aqueous solution, the concentration of hydrogen ions and hydroxyls are related to Kw. The product of the given concentrations would not equal Kw. So they're saying take this one, multiply by that one, and it's not equal to 10 to the minus 14. That's another way to do it. You can do it this way and say that's not equal to the value given here. There. Or you can multiply the two together and find that it is not equal to 10 to the minus 14. So that's the answer. Okay. All right, 73. Let's see if this one's different. According to Arrhenius, bases are species that produce what? Ions in aqueous solution. Hydroxide. That was Arrhenius' definition. The molecule itself must have a hydroxide in its formula in order to produce a basic solution. Right? Bronsted-Lowry came along and said, yeah, well, what about something like ammonia? It doesn't have hydroxyl. If you put it in solution, sure enough. And then there are other possibilities. I mentioned one earlier, the sodium hypochlorite, which is bleach. When you put that in solution, you get a basic solution. And we're going to talk about that in a few minutes. That's a salt, sodium and hypochlorite ion. We didn't talk about that though, did we? What's the definition? What's the definition in chemistry of a salt? In order to do that, you need to consider the reaction of an acid and a base. And we're going to use an Arrhenius base here. So this acid reacts with this base. Okay, that's an acid, that's a base, according to Arrhenius. It also fits Bronsted-Lowry too. And what does it produce? Well, this is a double replacement reaction. So these two cations swap places. This sodium comes over here, and that hydrogen goes over there. Okay? So this reaction, the acid-base reaction, will always produce a salt and water. That's the definition of a salt in chemistry. Reaction of an acid and a base produces a salt, which is a combination of this cation and that anion. The cation from the base, anion from the acid, combined make a salt. Okay? So, we'll talk about that a little more in a few minutes. I've just introduced the topic here. All right, 75. A conjugate acid-base pair consists of two substances related by the donating and accepting of what? Obviously, a proton. A hydrogen ion, which is essentially a proton. Okay, that's just a definition. An acid such as H2S that poorly conducts an electric current when dissolved in water is said to be what? It's a weak acid. Okay, that's one way of determining whether or not you have a weak acid or a strong acid. A strong acid dissolved in water will conduct electricity very efficiently. And if you have a light bulb in the circuit, it'll light up, it'll be bright. Whereas with H2S or acetic acid, right, or hydrocyanic acid, you'll get a very weak current and a very weak light in your bulb. So let's do 85, see with 85. A blank solution contains a conjugate acid-base pair through which it is able to resist changes in its pH. Okay, this is definitional. This is a buffered solution. It's got an acid-base pair and it resists the change in pH. All right. Let's see, we got any more ones? Nope, no more ones. So we'll go all the way back up to the top. There we go. So let me see, I need to check to be sure I'm not missing something at the top here. There we go, there's the ones. Okay, here's the first. Here's the first difficulty 2. All right, this one doesn't have a number. All right, consider a 0.25 molar solution of the following salts. For each salt, indicate whether the solution is acid, base, or neutral. Okay, we talked about that acid-base reaction. This is that was our jumping off point to answer this question. So if we have a salt composed of this cation and that anion, where did it come from? Right? That's barium perchlorate. That's the perchlorate polyatomic ion. So this would have originated from HClO4. And this would have originated from barium hydroxide. Okay. So the rule of thumb in determining the acidity or the basicity of a salt dissolved in aqueous solution. Say we start out with that salt. It's a solid. We put it in solution. It will go into solution. All perchlorates are soluble. When it goes into solution, what's the pH? Well, the rule of thumb is if it's derived from a strong base and a strong acid, you get a neutral solution. So this one will be neutral. All right. Let's see, what's this one? C2H5NH. C2H5NHBr. Okay, so what is this one derived from? This is a little more difficult. Look at this right here. This would have derived from HBr. So this part of that molecule is derived from a strong acid. Correct? HBr. This one would have been derived from C2H5NH2. So this is a strong acid and a weak base. The rule of thumb is if the acid is strong and the base is weak, the solution of that salt is acidic. All right, so we'll say acidic. How about this one? Na C6H5 CO2. Okay. Now, this one is not obvious the way it's put together. But if we do it like this, now what does that look like? That looks like a carboxylic acid group without its hydrogen. Right? Its hydrogen was replaced by that sodium ion. So actually, it would be better to write it like this. And that shows you that the sodium replaced the hydrogen that went with it. Now, when we do it that way, it's a little easier to understand. This would be derived from sodium hydroxide. And this would be derived from C6H5COOH. And that is benzoic acid. That's a weak acid. And this is a strong base. So you might guess that with a strong base origin and a weak acid origin, you get a basic solution. Similarly, sodium cyanide, HCN, HCN is a weak acid. So that's derived from a weak acid. This is derived from a strong base. So the solution is basic. Rubidium bromide. Rubidium. Rubidium hydroxide would be a strong base, and HBr, hydrobromic acid, is a strong acid. So this one should be neutral. Okay, let's see if I got them right. Yep. Okay, now I gave it to you in the terms of rule of thumb. When you have weak acid, strong base, it's basic. But the reason that it's basic is not because of the strong base. The reason it's basic is because of the source of the weak acid, the conjugate base of the weak acid. So let's look at sodium cyanide for example. Right? When you put this in solution, sodium cyanide, what does it do? It breaks up into sodium ions and cyanide ions, right? So is sodium going to react with water? No, sodium doesn't want a hydroxyl out of water, right? Sodium hydroxide is a strong base, so that sodium is, well, actually, sodium hydroxide is a strong base. Sodium doesn't want, well, it can't take a proton, and it doesn't want a hydroxyl because it just gave one up, right? Sodium hydroxide completely dissociates into these two. So that's a strong, well, you know, that's a strong base. That's a strong base too. So that's kind of, it only works with acids. Okay, so back to this topic up here. The sodium ion is not going to take a hydroxyl from water. It just doesn't happen. But that cyanide is derived from a weak acid, right? Weak acid produces a strong conjugate base. So now what's going to happen? When you put that salt in solution, that cyanide ion is going to react with water. It's going to take a proton from that water and produce hydrocyanic acid plus hydroxyl. There's your base. Because this is a strong base, when you put it in solution, it's going after a proton and leaves behind that base. So that's why sodium cyanide is basic in solution, not because of the sodium, but because of the cyanide. Now, I don't know if you're considering this possibility, but what if you have a salt derived from a weak acid and a weak base? Like this one. Ammonium acetate. What do you do then? Well, that's beyond this course. You need a little bit more information before you determine whether this is acid or base. You actually have to have numbers. You have to have a K value for that species and a K value for this species to compare. So we're not going to do that in this class. You just have the three possibilities for producing a neutral solution with a strong acid, strong base, or acidic with a strong acid, strong weak base combination, or basic with a strong base, weak acid combination. That's all you have to worry about in this class. Okay, 009. What do we got here? Multi-parts. In the following chemical equation, identify the conjugate acid-base pair. All right, this should be simple, right? And the only reason that is difficulty level 2 is because it has multiple parts. So this first part, which is the conjugate acid-base pair? Of this one. All right, so if we look at that equation, there's the acid and there's the base. The conjugate base of the acid is fluoride ion, and the conjugate acid of the base is ammonium. So let's see. That's an acid, that's a base, correct. That makes this a base and this an acid. That looks like the answer right there. So what else could you have? Well, here's an acid base. Let's look over here. Nope, that's not an acid. All right, so that first one is the answer. Let's look at the next one. If we're going to react this one with water, which one is the acid and which one's the base? Remember Bronsted-Lowry. Which one donates the proton? Water. Water is the acid, right? Because hypochlorite ion doesn't have a proton, but it's derived from a very weak acid, so that is a strong base. So water is an acid, so it's one of these two down here. And these are the base. Okay, that side is okay. What's the other side? This becomes the conjugate acid, and that's the conjugate base. Yes, this one should be the correct answer. Okay, how about the last one? Here's the HSeO3- ion and water. So what happens here? Notice that if you got this one on that side and you add a proton to it, you get this one. So that has acted as the base. HSeO3- ion has accepted a proton, and water has delivered it. That makes water the acid. Right? So water has to be an acid. It's either of these two in the middle. Okay, those two are correct on the reactant side. How about the product side? On the product side, now this one is the acid and OH- is the base. There you go. Okay. All right. So let's go down to this level 2. Choose the conjugate base for the following acid. Okay. We can do that. It won't take much time. So what do we need? We need to be sure that we're only losing one proton, and the conjugate base will be what's left behind with the charge difference. Right? So NO3- is what we're looking for. There. Okay. How about the next one? Conjugate base of this acid, IO3-. Okay. How about this one? Only one proton, remember, H2CrO4. This is chromic acid, right? CrO4 is the chromate ion, chromic acid, and then we need HCrO4-. HCrO4-. We don't even have to look at the others. They would just be confusing. How about this one? HAsO4-2-. Lose one proton, you get AsO4-3-. Okay. There we go. All right, how about 15? See if it's different. I'm going to skip this one. This is just hashing over the same stuff over and over again. Let's go down to this one. See if it's different. For the hydrogen ion concentration given below, calculate the pH of the solution and the concentration of the hydroxide ion in solution. Okay, this is a twist on the difficulty 1 that we used earlier. And it's got multiple parts. So we're going to do O47. All right. So for the A, we're given hydrogen ion concentration as 1.02 times 10 to the minus 8. All right. So how do we know how to find the pH, but suppose we want to find the hydroxyl concentration. We use the equilibrium expression for the dissociation of water. All right. So the K W is equal to 1 times 10 to the minus 14, which is equal to the hydrogen ion concentration times the hydroxyl concentration. If we substitute this one in here, now we have this mathematical expression. And we can solve for that unknown. We just say this is equal to that number divided by this number. So let's see, 1 exponent 14, change sign, and divide by 1.02 times 10 to the minus 8. Let's see, we got how many significant figures here? We got 2 there. Well, this can have as many as we want. This is a an exact number, 1.00000 all the way out. So we can have 3 significant figures here at 9.80 times 10 to the minus 7. All right, so let's put that one in first. All right, and then we can do the pH. I decided to do OH minus first because of this, and then we can calculate the pH separately. So the pH is going to be the negative log of 1.02 times 10 to the minus 8. Okay, 3 significant figures, we can have 7.991. Three decimals, 3 significant figures. 7.991. There we go. Let's see if they're right. Yes, indeed. Now, part B is a little different. Indicate whether the solution is acidic or basic. Oh, well, definitely. It's less than pH 7, so it has to be basic. Right? The hydrogen ion concentration plus the hydroxyl ion concentration is greater than 7, greater than 10 to the minus 7. It's greater than 1 times 10 to the minus 7 by a little bit. Well, actually, it's almost an order of magnitude. We're just a hair's breadth away from another factor of 10, which would make this 10 to the minus 6. So that would be a basic solution. Okay. All right. Let's see. The next number 2 difficulty is O51. Let's see. Calculate the hydrogen ion concentration in moles per liter for a solution with a pOH of 4.92. All right. This is a good one. All right. For A, if the pOH is 4.92, what's the most efficient way to calculate the hydrogen ion concentration? What I would do, rather than making 2 complicated equations, I'd use one and use a simple equation first, which means 14 equals pH plus pOH. So pH plus 4.92 and pH equals 14 minus 4.92, which is equal to, let's see, 8, 0, let's see, 2 minus 8, 0, 4, 9. See, is that right? 10, 1, 9, 10, 13, 14. That's right. So the pH is 9.08. This is a basic solution. Now, what's the concentration? Well, we need 10 to the minus 9.08. Will be the hydrogen ion concentration because that is the antilog of the negative value. Let's see. 2 decimal places means 8.3 times 10 to the minus 10. There you go. When I first started doing logs, when I was a lot younger, we had to look these values up in a table. And the table was arranged in certain increments. And if you needed to get finer than that, you had to interpolate, which is a fancy word for split the difference. And then soon after that came along slide rules. You may have never seen a slide rule. You have to go to a museum. A slide rule is based upon logarithms. That's how slide rules work. So it's easy for a slide rule to generate the log of a number or to do the antilog, either way. And then came along calculators. The first calculator I had was made by a company called Bomar. It quickly went out of business. But the calculator was about the size, about these dimensions, like that, but it was thicker. It was really thick and heavy. In fact, it was heavier than this one, and this one's pretty substantial. And the battery didn't last very long before you had to recharge it. And it would only do basic math, square roots, squares, and logarithms. So now we have calculators that are, I mean, they're as powerful as our first desktop computers used to be. Okay, so let's do the rest of these. Oh, I erased my answer, didn't I? What was it? 9 point, maybe it's in my calculator already. Oh, 8.3 times 10 to the minus 10. 8.3 times 10 to the minus 10. Oops, I forgot my sign. See what happens? 10 to the minus 10. Okay, let's see if I can do this one right. So we use the same procedure. POH, subtract 7.08 from 14. Okay, that's 6.92. Change the sign and power of 10. 1.2 times 10 to the minus 7. Let's see if I can get this one right. Minus 7. There you go. Now we're cooking. 12.68 subtracted from 14 is 1.32. Change the sign. That's our power of 10. 4.79 times 10 to the minus 2. I think I had an extra decimal there. Well, it rounded off. Okay, 1.74. I have 2 decimals, so we can have 2 significant figures. Okay, so my mistake. 2 decimals means 2 significant figures in your molarity. Let's see, 14, 1.74 subtracted from that, 12.26. And now that becomes, the negative of that becomes a power of 10. 5.5 times 10 to the minus 13. I was about to do it again. Minus 13. There we go. Okay, so I missed that one because I forgot my sign. 10 to the minus 10 here. All right. So that was 51. Let's see, is 52 different? Calculate the hydrogen ion concentration in moles per liter for, no, that's just more of the same. So we'll skip that one and go down to the next difficulty level 2. Here we go. Acid-base equilibrium concepts are developed in this chapter in aqueous solution. Water is the solvent is intimately involved in equilibrium. That's true. However, the Bronsted-Lowry acid-base theory can be extended easily to other solvents. One such solvent is ammonia. Choose the chemical equation indicating how HCl behaves as an acid in liquid ammonia. Okay, I'll go with that. So this is 065. A non-aqueous solution. So we've got hydrogen chloride dissolved in liquid ammonia. So what does it do? Well, does it tell us? This is going to be the proton donor. Why? Because of the difference in electronegativity. This chlorine is pulling electrons to itself very strongly, and that weakens that bond to make a proton. Whereas these hydrogens bound to the ammonia molecule are very strongly and covalently bound to that molecule. But notice that plus and these are lone pair electrons. That's the structure for ammonia. That plus is going to be attracted to those negatives. And as a consequence, you get the ammonium ion. All right. So those two pair electrons form a bond with that hydrogen. Okay, so that being said, now how is the reaction going to proceed? This is the acid, that's the base. So we're going to have a chloride ion and an ammonium ion. This is the conjugate base. This is the conjugate acid. Okay? That's a strong acid, that's a weak base. So that makes this a weak base, and that's a strong acid. That ammonium wants to give up its proton fairly readily. Anyway, let's get back to the question. Choose the chemical equation indicating HCl behaves as an acid in liquid ammonia. So, which one? Well, let's see. We got HCl and NH3 right here. We've also got it here and here, right? The second one can't work. So, what do we get? Well, if we do it chloride and ammonium, that's the first one. The others don't work. Okay. Now for the second one, choose the chemical equation indicating how hydroxyl behaves as a base in liquid ammonia. All right. Remember, if we put hydroxyl in there, where did it come from? Its origin is water as an acid, giving up its proton. It's a weak acid, which makes hydroxyl a very strong base. So if we add hydroxyl, this becomes the base, correct? OH behaves as a base in liquid ammonia. This becomes the acid. So that means this has to donate a proton, NH2, and now it loses a proton, makes it 1-. And that proton goes over here and makes water. Okay, so now this is the conjugate base of that acid, and this is the conjugate acid of that base. All right, let's see which one matches. OH and ammonia. Okay, first one, first one, third one, and fourth one are good for reactants. How about products? We got water. There's water. And there's water. So the second one or the last one. And then our species over here. Okay. My mistake. No, wait a minute. That can't be. If it's liquid ammonia. Okay. Oh, here it is. There it is right there. Ammonia, water, there. Right? That's the way ammonia would act as an acid. You know, it just occurred to me, can ammonia be amphoteric like water is? Could it be like this? With pure ammonia, transfer one to the other, is that possible? Probably. Right, it could do that. But I don't know what the K is for that one. Right? This would be a pure liquids. So it would be a product of that one times that one. Just like we had protons times hydroxide for water. So I need to look that up. I'm just curious, you know, curiosity is your friend. But it seems this expert program likes that answer, so we're going to go with it from now. Simply because the question dictated the terms. All right, let's see, this one. Buffered solutions are mixtures. All right, we did this one earlier. Explain why mixtures of HCl and Cl- are not buffered. So let's see what they like. Let's see if we can find one that's close to the explanation I gave you earlier. All right, the conjugate acid of a strong base is capable of strongly attracting protons. No, it's not. The conjugate acid of a strong base, would donate protons. The conjugate base of a strong acid is capable of strongly attracting. Definitely not that one. The conjugate base of the strong acid is Cl minus right here. And that Cl minus will not attract protons. How about the conjugate base of a weak acid is capable of strongly attracting protons, but the conjugate base of a strong acid does not have a strong affinity for protons. That's the best answer right there. All right, that was 69. I didn't even write that one up there. So let's go down and find the next number 2. Here we go. 83. Let's see if 83 is different. 0.21 molar HCl solution contains, all right, well, this is nothing new, but it's so easy, we'll just do it. 0.21 molar hydrogen protons and 0.21 molar chloride ions, because it completely dissociates. Okay, that was simple. How about 87? When hydriodic acid, HI, is added dropwise to a buffered solution, blank of the buffer consumes the added hydrogen ions. So, and this is a generic question. Which part of the buffered solution reacts to the added protons? This is a strong acid, so it's going to be completely dissociated. Those free protons that are floating around are going to be attracted to what? To the strongest base available. And if you've got a buffer with a weak acid producing a strong conjugate base, it's the strong conjugate base that is attracting the protons. The conjugate base component will react with the protons. All right. Let's see if this one's worth looking at. In the following chemical equation, identify the conjugate acid-base pairs. All right, we did one of these earlier, and I don't see anything odd about this one. This one's propylamine, which probably means nothing to you, but it's a organic compound. Okay. Choose the conjugate base for the following acid. We've done those before. Let's not waste your time on it. All you have to do to find the conjugate base is remove one proton and augment the charge. Because if you're pulling a proton away, that's a plus charge, you leave a negative behind. So you increment the negatives up 1. How about this one? Which of the following bases have relatively strong conjugate acids? Okay. This might be worth looking at. 093. So H2PO2 minus is a base. H2PO2 minus relatively strong conjugate acids. So if we add a proton to that, H3PO2. That's a weak acid. It's not a strong acid. A strong acid is what? Strong acid would be, well, you know, not even that. Phosphoric acid is not a strong acid. It's a slightly weak acid, but it's not a strong. So that one does not have a strong conjugate acid. How about HSO3 minus? HSO3 minus would be H2SO3. That's a strong acid. Sulfurous acid. HBrO4, well, let's see, we start off with this one, and then the acid would be HBrO4. That's perbromic acid. That is definitely a strong acid, a very strong acid. And this one, IO4 minus, makes HiO4. So that's periodic acid. That's a strong acid too. Now, I could be wrong on this one right here. Let's see. It'll probably tell me right off the bat. Yeah, it says I'm wrong. So bases that are weak have relatively strong conjugate acids. So you look for the weak base. Oh, I misread the question again. Let's do that over again. Try another version. Try another version. Okay. Which of the following bases have relatively strong conjugate acids? All right. HClO4 is a strong acid. H2SO3 minus, I don't think so. HBr is strong. Chlorous acid is not strong. So let's see if that one. Okay, it liked that answer. The logic is right. I just misread the question. All right. So that was number 2. Which one is this? There, number 2. How about this number 2, 97? Calculate the pH of the solution indicated below. That's too simple. It's multiple parts. Maybe we better do that, see what the second part is. So let's take 1.08 times 10 to the minus 3. Take the log of it, change sign. So that's 2.97 pH. All right. And part B is a solution acidic or basic. Well, it's a greater number than 10 to the minus 7th, plus the pH is less than 7. So that's acidic, definitely. All right. Let's scooch up a little bit, and let's look at this one and see if it's worth tackling. Calculate the pH corresponding to the hydroxide ion concentration. We did one of those before. We don't need to do that one again. Calculate the pOH corresponding to the pH value. All right. How would you approach this one? We've done one like that before, but slightly different twist. If the pH is 1.48, what is the pOH? It's 14 minus 1.48, right? So it'd be 2, 4 from 9 is 5, and 1 from 13 is 12. 10, 10, 1, 4, 3, there. So the pOH is 12.52. Okay, and indicate whether the solution is, well, obviously it's acidic. It's less than 7, correct? All right. How about this one? Okay, this one is level 2 because it's got so many parts to it. For the given solution, calculate the concentration of the complementary ion, the pH, and the pOH. Complementary ion, they mean, is hydroxyl if it's hydrogen ions if it's hydroxyl. So to do this one, you would divide 9.05 times 10 to the minus 4 into 1 times 10 to the minus 14. So let's do that. 9.05 Let's see, I better write this one up here. 100. Okay, 9.05 times 10 to the minus 4, and divide that into 1 times 10 to the minus 14. That's based upon, right, that same formula, P, K, well, no, actually it's KW, excuse me, KW equals that's 10 to the minus 14. So if you know, if one of these is unknown, you just take the known one and bring it over here and divide. So that's what I'm doing. So it's 1.10 times 10 to the minus 11. 1.10 times 10 to the minus 11. There you go. Let's go ahead and do POH, because that would just be the negative log of that value. So we'll take the log of it, change the sign, and we have 3 significant figures, so we can have 10.957. Okay, and the pH is going to be 14 minus that number. Which is 3.043. There we go. All right. And if we do this one by the same token, we would divide 4.21. Let's see, let me go back. And there we go. And divide this number into 10 to the minus 14. Minus 5, and divide that in. So that's 2.38 times 10 to the minus 10. Oops. Get my cursor in there. Minus 10. And then the pH would be the negative log of that number. Let's see, 9.62. Right? And then subtract that from 14. 4.38. There we go. And it did like my answers. So let's see about 101. Do we want to do 101? Calculate the hydrogen ion concentration. That's nothing new. Let's skip that one. That's nothing new either. How about this one? All right. We've done one like this before. You just, if you want to know the hydrogen ion concentration, the simplest way is subtract this from 14 and do the antilog of the negative. That one's really simple. So let's go back up to the top. Let's see. Here. Let's go back up and look for level 3. Strong acids and bases, level 3. All right. Complete the table for each of the following solutions. Omit molarity units for your answers. You know, that's nothing new either. Right? This strong acid, this strong base. All right, we'll do this one just because we can. All right, so if you have, and that one's not going to have a number, because that's a chem work, 0.0060, 0.0060 molar nitric acid. Okay, so what is the hydrogen ion concentration? It's the same, right? It's the same. So I think this system will accept either standard notation or scientific notation. So 0.0060 there. And the pH would be the negative log of that. The negative log of 0.0060 log change sign. So we have two significant figures. Our pH can be 2.22. All right. POH is that subtracted from 14, which is 17.78. No, that's not right. Subtracted from 14. .78. There we go. And then to get the P, that's the POH. Now to get the hydroxyl ion concentration is 10 to the minus 11.78 power, which is, let's see, 1.7 exponent to the minus 12. Okay, now we got to do this one. 3 molar KOH. This is going to be a monstrous concentration. So it's 3 molar, excuse me, that's not right. It's 3 molar hydroxyl. All right. So the POH of hydroxyl is 3 log change sign. So that's negative, two significant figures, negative 0.48. Negative 0.48. The pH then would be 14 minus a minus. So it's 14.48. Right? And then the hydrogen ion concentration would be 14.48. Change the sign. Power of 10. 3.3 times 10 to the minus 15. Okay, so notice when I had the concentration here, I worked from the hydrogen ion end across. But if we're starting with hydroxyls, then you need to start from the right end and move backwards the other direction. Okay, that was level 3. Let's find another level 3. Level 3. Hold on a second. I'm going to have to come back to this. And the reason is, maybe I won't have to. Let me look. Yeah, I can do it this way. There we go. Okay. Now if any students come, they can just pop right in. Okay, here's level 3, number 3, difficulty 3, 094. Okay, calculate hydrogen ion in the following solution. That's nothing new. How about this one? Calculate hydroxyl in the following solution. That's nothing new. I don't know why they make that difficulty 3. That's not difficult at all. How about this one? We might finish early today. Calculate the hydrogen ion concentration and the pH of the following solutions of strong acids. I'm going to take a quick look over here in these other problems and see if there are any 4s. No, I didn't put any 4s there. Okay, that's good. All right, so we'll do this one and call it a day. But first, I need a bathroom break. I'll be right back. I had to take a short break. We've really only got one problem left. There are no difficulty level 4s in here. So this is the last level 3. And it's not a whole lot different than others that we've done, but I thought I'd just finish off the day with this one, kind of cap off the discussion with 16.104. Okay, so we're going to calculate the hydrogen ion concentration and the pH of the following strong acids. So 1.15 times 10 to the minus 3. 1.15 times 10 to the minus 3 molar HClO4. So the concentration of hydrogen ions here is exactly the same. That is a strong acid. Perchloric acid, minus 3. And then the pH is just the negative log of that value. 1.15 exponent 3. Sign, log, sign again. So we have 3 significant figures. That means 2.939 is the pH. 3 decimal points. Okay. B, 6.6 times 10 to the minus 5 molar. Nitric acid, that is a strong acid also. So the concentration is going to be 6.60 times 10 to the minus 5. And we punch that into our calculators. All right, and take the log of that. Change the sign, 4.180. 4.180. All right, and we got 2 more. Hydrochloric acid, I'm not even going to write that one up there. 1.40 times 10 to the minus 2. And then we take the negative log of that value. And we have 3 significant figures, so we can have 1.854. 1.854. And the last one, HBr is a strong acid, of course. 1.90 exponent to the minus 3. So let's punch that one in. 1.90. Yep, exponent minus 3. Take the log of that, change the sign. 2.721. Okay. Now, one final point. We covered this in our in the lecture. What if we dissolved perchloric acid in aqueous solution, and we added enough of this to make a solution that was 3.01 times 10 to the minus 9 molar. What would be the pH of that solution? Well, how much hydrogen ion do you have in there already? You've already got 1 times 10 to the minus 7 molar from the dissociation of water, right? And that's about 2 orders of magnitude higher than this one. So what's the pH? The pH is 7. Now, I wasn't paying attention when we went through all these problems if there were any where the hydrogen ion concentration was less, but the hydrogen ion concentration can be less than this if you add base, right? But if you add acid, at that amount, you're not going to exceed this one. I mean, there will be some more hydrogen ions in there. I don't doubt that. But you haven't shifted the value here by much, right? If we make this one comparable to that, right, that means we need to move this one over like that. Correct? 2 places, 2 places. So now if you add these together, 1.0301 times 10 to the minus 7. Let's just do that one, right? You've added that one to already existing. So 1.0301 exponent 7, change sign, log, there. That didn't work. Hold on a second. 1.031 to the negative 7 power, then log, then change the sign. Right? 6.987. That's the actual pH, right? You'd need an extremely sensitive pH meter to detect that difference. Okay. Now, when you add an acid to water that is 10 times more concentrated than the water hydrogen ions, then you can ignore water and calculate based on the added acid. Okay, that's all I have today, and we're finished way early, right? We could go to 11:50, but it's 11:20. That's a half hour early, which is, it's okay. I mean, we've covered all the bases, and what we'll do next Tuesday is we'll pull out the review document and work the problems in the review document. There'll be a lot of overlap, right, between what we were doing then and now, but there may be some questions in there that test your knowledge even further. So that would be a good place to concentrate, work the rest of these problems. There are not a lot of them. There are only 18. Finish those up and then pull out that review document that's in Blackboard and work those problems. Then if you have any questions on next Tuesday, we can iron out any problems and you'll be ready for the exam on Thursday. And then after that, we have just 1 chapter left, plus the final, of course. Okay,